A concept intimately related to electric fields is electric potential. Recall that the electric field is the force per unit charge. The electric potential is the energy per unit charge and is often designated by the letter V. Notice that the electric field is a vector, while the potential is a scalar quantity. Since scalars are usually easier to work with than vectors, it is sometimes simpler to solve a problem using electric potential rather than electric field. Electric potential has its own unit, which is known as the volt. 1 volt is equal to 1 joule per coulomb. Strictly speaking, the work done moving a charge from point A to point B is equal to the electric potential at point B minus the electric potential at point A. Often, point A is considered to be at a large or infinite distance from all charges that produce an electric field, and the electric potential, V sub A, at this infinite distance is taken to be zero. Note that the choice of a zero potential at infinity is taken arbitrarily and for simplicity. The work done moving a charge from point A to point B can be positive, negative, or zero. Thus, the potential at point B can be higher, lower, or equal to the potential at point A. For example, in order for a positive test charge to be brought closer to an isolated positive charge, work must be done by an external agent. The work done in this case is positive. In this case, the electric potential at point B is higher than at point A. On the other hand, if the isolated charge is negative, a positive test charge must be restrained to keep it from moving from point A to point B, and the work done is negative. In this case, the electric potential at point B is lower than at point A. The potential difference does not depend on the path followed when the test charge goes from point A to point B. Consider the positive test charge moving from position A to position B along the arbitrary path that is shown. Recall that the work done on an object at some point is the dot product of the force and the path vector. To move the positive test charge towards a positive charge, an external force must be provided in the radial direction, since the repelling electric force points in the radial direction outward. If the path vector is broken into a radial component and a transverse component, you can see that work is done only along the radial segment of the path. The total work done along this path is found by summing up all of the segments along the path, or equivalently, integrating over the path from position A to position B. Now let's choose a different path from point A to point B that is in the radial direction and label this as path 2. Once again, the total work done is found by integrating along this path. Notice that work done along path 1 is the same as the work done along path 2. Since the first path was chosen arbitrarily, this shows that electric potential is path independent. Consider the path of a test charge that follows a line at right angles to the radial direction. We can calculate the work required to move the charge along this path in the usual manner. Since the force vector and path vector are at right angles, the dot product is 0 along the entire path. Thus, the total work from point A to point B is 0. The potential difference between point A and point B is the work done per charge along this path, which is 0. Thus, the potential at point A is the same as the potential at point B. Since the electric potential along this path does not change, it is called an equipotential surface. For a point charge, equipotential surfaces are circular around the charge. This is because the electric field points in the radial direction at all points from the charge. Let's consider the implications of an equipotential. Along an equipotential surface, there is no change in potential and thus no work is done on a test charge along this path. Thus, if the test charge was somehow constrained to move only along this path and released at rest, it would remain at rest. From one equipotential surface to another, however, the potential is different, and work will be done on the charge by the electric field. Now, if the charge can move freely in any direction, it will be accelerated from one potential surface to another by the electric field. Since the movement of electrical charges represents a current, this tells us that currents flow not along but across equipotential surfaces. For the Van der Graaf generator seen here, an electric field is created that points approximately radially away from the outer surface of the generator. Which of the images best depicts the equipotential surfaces for the Van der Graaf generator? Correct. Since the electric field is in the radial direction, the potential surfaces follow the surface of the sphere. Which way would you orient a long light bulb near the Van der Graaf generator in order for it to light up? Correct. Now let's test if this is really true. Notice that along the equipotential, the bulb doesn't light up, but when placed across the potential, it lights up, even if it's not plugged in. We will now relate the electric field and the electric potential directly. Consider a positive test charge placed in a uniform electric field as shown here. Since the electric field is uniform, the work required to move the test charge from position A to position B is the force times the distance. Recall that the electric force that acts on the charge is given by the charge value times the electric field, which we substitute into the work equation. The potential difference between A and B is given by the work divided by the charge. Thus, the potential between A and B is given by the electric field times the distance. The potential difference can be written as the change in potential, which in mathematical terms is called delta V. This can also be written such that the electric field equals the change in potential divided by the distance. In this form, you can see that another unit for the electric field is the volt per meter. This expression holds only for a uniform electric field. We can derive a more general relationship when the electric field is not uniform. To do this, we go back to the expression for the work done on a charge along a path from point A to point B in a non-uniform electric field. As usual, the total work is the integral from the work done along the entire path from point A to point B. The force that must be exerted to move the charge is equal and opposite to the electric force and is equal to negative Q times the electric field. We now use the expression for electric potential and bring the charge out in front of the integral. The charges cancel, and we get the general relationship between the electric potential and the electric field. Going back to the uniform electric field case, we can use the general expression to find the potential difference between point A and point B. The dot product between the electric field and the path introduces another negative sign that cancels the overall negative sign, and the uniform electric field can be brought out in front of the integral. The integral is just the distance between point A and point B, and we get back the expression that we found before. We now calculate the potential of a point charge. Imagine our test charge brought from point A to point B along the radial path as shown. The potential difference between points A and point B can be found from the electric potential and electric field equation. The electric field points in the radial direction away from the charge, which is in the same direction as the path vector. Now substitute the electric field for a point charge that we found previously and move the constants out in front of the integral. The integral can be evaluated giving an expression for the potential difference between point A and point B. If point A is moved to infinity, where the potential is assumed to be zero, we find a general expression for the potential at a distance r from a point charge. Notice that the potential of a point charge goes as 1 over the distance from the charge, compared to the electric field, which you probably remember goes as 1 over the distance squared. The potential for a group of point charges is simply the sum of the potential for each individual charge. The value, Q sub m, is the value of the nth charge at a distance of r sub n. If instead of a group of point charges, the charge is continuous, the summation is replaced by an integral where dV is the potential due to a charge element dQ. Now we will derive the potential of a uniformly charged disk along the axis of the disk. First consider a charge element, dQ, on a flat circular strip of radius y and width dy. The charge in this strip will be equal to the charge per unit area multiplied by the area of the strip. The disk is uniformly charged, so the charge per unit area is constant. The symbol sigma is used to represent the charge per unit area of the disk. The area of the strip is given by 2 pi times y times dy. The potential due to the charge strip at a distance x along the axis can be found by using the potential expression previously derived. Substitute for the charge element dq that we have already found and for the distance r from the disk to the point x along the axis. Integrate over all of the charged strips from 0 to a to find the potential at distance x due to the disk. To simplify the integral, cancel out like terms and move all constants in front of the integral. Perform the integral over y, noticing that the x in the denominator does not depend on y. If x is much larger than a, it can be shown that this expression reduces to the potential of a point charge. Recall that a dipole is created by a positive and negative charge separated by a distance 2d. At an arbitrary point P as shown, the potential can be found by adding the potential due to each charge. Using the distances from each charge as labeled, we find an exact expression for the potential at point P. If the point P is at a large distance from the charges compared to the separation distance between the charges, an approximation can be made for the potential. First notice that for the angle theta as shown, the difference between R2 and R1 is approximately equal to 2d times cosine theta. Also, the product R1 times R2 is approximately R squared. Put these into the expression for the potential. Earlier, we identified 2dq as the dipole moment P. Using this notation gives a final expression for the potential at a large distance from a dipole that depends on the angle theta with respect to the dipole axis. Notice that at an angle of 90 degrees, the potential is zero regardless of the distance r from the dipole. This represents an equipotential surface, since the potential is the same everywhere along this line. Equipotential surfaces can be found at other locations as well. If the electric field lines are drawn for the dipole configuration, notice that at every point the electric field is perpendicular to the equipotential lines.